All right, this video is really going to start off our discussion of heat and thermodynamics. Before we get to that, we need to define what heat is and what it's not, and temperature. I could ask you what you think heat is, and quite frankly, a lot of people don't really have a good concrete definition of heat in the scientific sense. So we need to be specific about what heat is. I think we could all agree that if we had two objects, one hot and one cold, that the hot object would end up becoming colder and the cold object would end up becoming hotter if they were in contact. And that's because of the first law of thermodynamics, which we'll talk about later. But the reason is, everyone would agree that heat actually gets transferred preferentially from the hot object to the cold object. And that actually brings us to probably the best definition of heat that we can give. Heat is simply that energy, the energy transferred from a hot object to a cold one. The energy transferred from a hot object to a cold object. We call that heat energy. And we're going to talk specifically about what that is. Well, we'll talk about that when we get to temperature. What heat is not is very important, because many times when you ask people what heat is, most people will bring the temperature concept into the discussion. But really, the temperature concept doesn't necessarily come into discussion when we're defining heat, because heat is not the same thing as temperature. And it's very important that you remember this, that you understand heat and temperature are not the same thing. They're related in that temperature can be a measure of heat, but heat and temperature are not the same thing. We're not transferring temperature from one object to another. We're transferring energy, and that energy we refer to as heat. The best definition of temperature I can give you is this, and I'll write it and I'll explain it. Temperature is a measure that indicates, and this is a longer definition, you may have to write small. The measure that indicates the average kinetic energy of the molecules of the substance. Because we need to understand this concept of heat and temperature, and the fact that a hot object has a higher temperature because it has more heat energy contained in it. And that energy is in the form of these molecules. You see, if we have a beaker of, let's say, water, and you have a bunch of molecules in here, I think you all know that these molecules are not just sitting there, they're all moving around in random directions. And you know from our discussion of energy that when anything is moving, it has kinetic energy. And kinetic energy is related to mass and speed. Therefore, the faster these molecules are moving, the more kinetic energy they have. And the more energy they have, the more energy they can transfer to an object with not so much energy. In other words, an object that is cold. So a hot object simply has a lot of kinetic energy in its molecules. Its molecules are moving around very fast. They're more random. They're quicker, they're harder to, pin down, I guess you could say. So temperature is a measure that indicates the average kinetic energy of one molecule in this substance. Not all molecules are going to have the exact same kinetic energy. They're fairly random, but generally, as the temperature increases, the average kinetic energy of all of those molecules will increase. All right. So when we talk about temperature, temperature isn't the measure of energy, it's a measure that indicates that energy, right? So when we measure degrees, these aren't energy measurements. Remember that heat is energy, and all energy is measured in joules, right? But temperature is an indication of the amount of energy, the relative energy that we have. When we talk about temperature, we need to understand that in this class, in all science classes, we use mainly Celsius and Kelvin scales, no Fahrenheit. Fahrenheit is the one we're used to in the United States, and I'll explain in a minute why Fahrenheit is stupid. The guy that came up with it wasn't, but unfortunately, it's kind of random. We need to understand Celsius and Kelvin and how to convert between the two. The formula is in your formula chart, and it's number 60. And it basically goes like this. Kelvin equals degrees Celsius plus 273. It's real simple. If you want to go from Celsius to Kelvin, you simply add 273. If you want to go from Kelvin to Celsius, you subtract 273. So take a minute and look at these right here and do those on your own. Pause the video and see what you can come up with converting those temperatures. All right, for this one, to go from Celsius to Kelvin, that's what we're doing on this row. To go from Celsius to Kelvin, remember, all we have to do is add 273 for all these. So this would be 273 Kelvin here. 100 plus 273 would be 370 Kelvin, 373 rather, and negative 270 Celsius. Negative 270 plus 273 gives us 3 Kelvin. Now it's important, I think you heard me say this, when we talk about Celsius, we say degrees Celsius. That's what that little symbol is there. But when we talk about Kelvin, there is no degrees. We just say 273 Kelvin, 373 Kelvin, 3 Kelvin, etc., etc. And then on the other side, to go back the other way, we would simply subtract 273. So 100 minus 273 gives us negative 173 degrees Celsius. We have negative 273 degrees Celsius, and 373 minus 273 gives us 100 degrees Celsius there. You might notice at this point that we didn't have any negative Kelvin temperature. You might want to write that. No negative Kelvin temperatures. And that's not just because of these numbers we had. That's because it's not possible to have a negative Kelvin temperature. It's simply not possible. And the reason why is this. That's what this question is. Why can there be no temperature below 0 Kelvin, below absolute zero? We call this 0 Kelvin. The official term for it is absolute zero. And I'll explain what I mean by that actually in just a minute. But first, before we explain this, let's talk about these 3 scales that we most commonly use. I want you to look somewhere on the internet. You can just Google this stuff, find the temperatures, and label the boiling points and freezing points. Boiling points up here, freezing points down here, of water, of specifically water, on these thermometers. Take a minute, pause the video, and look that up and see if you can find those temperatures. All right, temperatures you found should have been along these lines. Fahrenheit is probably the most common to us. We understand that freezing point of water is 32, and hopefully you knew boiling point is at 212 Fahrenheit. But really, I don't really care if you knew those or not. The only reason you're going to need to know those is perhaps if you're cooking something, because every recipe in the United States involves degrees Fahrenheit. But in this class, Celsius and Kelvin is what we're really going to be concerned about. There is a conversion to go from Fahrenheit to Celsius, and it's got all these funky fractions and stuff in it. I don't care about that. We're not ever going to go from Fahrenheit to Celsius in this class because we're moving on to the more standardized temperature scales, the ones that make more sense, and that's Celsius and Kelvin. 0 Celsius, hopefully you know, is the freezing point of water, and 100 degrees Celsius is the freezing point of water. Hopefully that's familiar to you from chemistry. And then to go from Celsius to Kelvin, we simply add 273, so we get 273 Kelvin for freezing point, 373 Kelvin for boiling point. Again, these are the 2 that I want you to capitalize on, to pay attention to. You should